Hey folks, we're into section 2-2 looking for shortcuts, perpetuities, and annuities. So let's just establish this. We're still talking about the time value of money in this section. We're still talking about present and future value in this section. We're still talking about the net present value of projects in this section. Here's what's new. We're going to look specifically at cash flows called annuities and perpetuities. And we have shortcut formulas for annuities and perpetuities. So we need to ask ourselves, what is an annuity? An annuity is an asset that pays a fixed sum each year for a specified number of years. So in this particular example, you would deposit a certain amount of money into an annuity account, and the annuity account would then pay you out a fixed payment, an unchanging amount each year for the next 60 years until your death. That's an annuity. So let's take a look again at this problem that we had looked at earlier. You have to pay $12,000 a year in school fees at the end of each year for the next 4 years. If the interest rate is 8%, how much money do you need to set aside today to cover these bills? In other words, you know the future outflows are going to be $12,000 a year in years 1, 2, and 3, and 4. How much do you have to put in the bank account today to pay for all that? Well, here's how we calculated it in the last section. We said $12,000 times 1 divided by 1.08 to the first power. That took care of discounting the $12,000 from the first year back to time 0. And then 12,000 times 1.1 divided by 1.08 to the second. In the second year, that took the $12,000 the second year and turned it into year 0 money, present value money. All right, and when we added up all 4 of those cash flows, all discounted by their proper discount factors, the amount we had to set aside today, the present value that we had to put in today, was $39,746. Well, what you'll notice is we have a fixed number of payments, 4 years, regular fixed payments of $12,000 a year. That's an annuity. That's a 4-year annuity of $12,000 a year. So we have a shortcut formula we could use for that. Now, it may not feel like a shortcut formula when I show it now, but it is as we go further in this class. So here's the formula you're going to want to write down for the annuity. The present value of an annuity is the cash flow in year 1. If this is time 0, it's basically the cash flow from next year, times 1 over the discount rate minus 1 over the discount rate times 1 plus the discount rate, to T being the number of years that the annuity is going for. So just some terminology. That letter R, the opportunity cost of capital, that's called your discount rate whenever you're talking about discounted cash flow analysis or time value of money. That whole term that you're multiplying times the first year cash flow is called the T-year annuity factor. And T is the length of the annuity, in this case 4 years. So back to our problem. We can alternatively look at calculating the present value by this formula. Now we just need to know what to plug in. Well, what do you think you're going to plug in for the cash flow in year 1, right? We're at time 0. What about the cash flow year 1? Well, obviously it's $12,000. You can see that in the line column titled 1. How about the discount rate? What discount rate we're going to use? Well, that's in the problem. It's an interest rate of 8%. So we plug in 0.08 wherever we see R. In case of 1 plus R, that's 1.08. And then what's T? T is the number of years, the number of fixed payments, right, that we're going to have here. In this case, there's 4 of them. All right, now we plug that in our calculator, and we discover that our present value is $39,746, exactly as we saw before. All right, so let's revisit another problem from section 2.1. You're looking for an investment property. A house in Sabino Canyon is selling for $450,000. You think you can sell the house in 3 years for $550,000. You think this investment is about as risky as the stock market, and you could rent out the property for $1,500 a month or $18,000 a year for the next 3 years. should you make the investment? We're doing an NPV analysis here, right? We want to be NPV positive. Well, we calculated the NPV earlier, and here is what we saw. We saw that we would take the 450 as a negative number because it's an outflow. You don't have to discount it because it's the outflow today. It's in year zero money. Then each of the 18, we would have to, and those are in thousands of dollars a piece, so 18 would be $18,000, right? Take each of these 18s and we have to discount them at their appropriate discount factor. The 1 year, the 2 year, and the 3 year appropriately. And then we would sell the property a year for $350. You're gonna have to multiply that times the 3 year discount factor. What we got was $799, or in this case, $7,990. We can alternatively look at this thing as there's a cash outflow, there's a cash inflow, outflow of 450 in time zero, inflow of 550 in year 3, together with an inflow that is a perpetuity, a 3-year perpetuity, bringing in $8,000 a year for each, a fixed payment for 3 years. So if you'll look, I write again the net present value with the negative 450 out and the 550 in discounted at the 3 year discount factor. But in place of the 18s, with multiplied each times the discount factor, we have the annuity formula. So how would you fill it in? What would be the cash flow for year 1? Well, I think you know it's 18,000, which we'll just put in as 18 here, right? And then how about R, the opportunity cost of capital or discount rate? What's that going to be? All right, that's 10%. And then finally, what do we need to put in for T? What does T represent again? Well, it's the number of years the perpetuity will make payments for, which is 3 years. And if we go ahead and do that calculation, we discover $799 or $7,990 again, which is what we'd expect. So this is a useful shortcut whenever you have an annuity. And this brings us to our next idea, which is that of a perpetuity. A perpetuity is like an annuity, but it doesn't end after a fixed number of years. It goes on forever. It goes on for eternity. It goes on in perpetuity. So in our example here, we deposit a certain fixed amount at time zero into a perpetuity account, and then out will come these cash flows that are fixed, that are a regular amount every year forever. I know it's highly theoretical, but it's something we can value. The math exists for it. This is a perpetuity. So again, we have a perpetuity shortcut formula, and it's so simple. Now the present value today is going to be the cash flow a year from now, that first payment, which of course it's the same dollar amount for every payment in a perpetuity. So just that first payment in year 1 times 1 over the discount rate. That's it. Easiest formula in all of discounted cash flow. Some terminology to remember: R is the discount rate, and 1 over R is the perpetuity factor. So let's look at an example together. The year is 2040. Elon Musk has successfully transformed the automotive, power generation, housing, and commercial space industries. He is the first trillionaire in history. With his vast fortune, he creates an endowment to fund explorations of the universe. He structures the endowment to provide $100 billion per year for space exploration in perpetuity, starting in the year 2041. Stock market is still returning 10% per year on average. How much does Elon need to deposit into the endowment fund in 2040 to fully fund this endowment fund? Well, what formula are we going to use? This is clearly a perpetuity. It's going to be $100 billion paid out by the fund that he establishes for space exploration every year forever. So, cash flow in year 1, well, what's year 0 here? 2040. What's year 1 for cash flow for year 1? 2041. $100 billion in that year. Always $100 billion, but it's $100 billion in that year. Divided by what discount rate? The stock market. He's going to invest in the stock market. He's a wise man. So 1 divided by 0.1% times that $100 billion in cash flow. Now, it's one thing to write 100 billion as 100 and then B-I-L-L-I-O-N. It's another thing to remember how many zeros you got. All right, so you get familiar with that's 100 billion. What do you get if you do this division? Well, looks like we get $1 trillion. In other words, if Elon Musk wants to fund an endowment that will pay generously out $100 billion for space exploration every year for all eternity, he will have to invest $1 trillion into this account in year 0, which is the year 2040, and it will continue to make 10% per annum return through the stock market, which will continue to allow it to fund $100 billion a year forever. Interesting. Well, the only thing left to do for you, those who appreciate math, well, for all of you, but especially for those of you who appreciate math, is try to understand where we get these formulas from. Let's start with the derivation of the annuity formula. This should say the derivation of the perpetuity formula. The perpetuity formula, we'll start with that. Okay. Well, we know in a perpetuity, the cash flow in year 1 is the same as the cash flow in year 2 and cash flow in year 3 because it's always the same cash flow every year. So I'm just going to call it C for the ease of this calculation. And the first year's payment, it would be at a 1-year discount factor, second year to second year factor, discount factor, third to third year discount factor. So that's what you see going on in the first line. What's happening then in the second line? Well, it looks like I factored out a C times 1 over 1 plus R, leaving us with this series 1 plus 1 over 1 plus R to the first, plus 1 over 1 plus R to the second, so on and so forth. What does it look like I'm doing after that? Looks like I'm doing a U substitution. This is where I simply name 1 over 1 plus R U, right? I'm nicknaming it U. So that's what I've done here, and you can see that that matches up. Then, in the fourth and final line on this page, I multiply both sides of the equation by U. Hang with me, math folks. All right, now comes the mathematical trick that happens a lot in derivations. Take that last equation we had minus the equation you had right before it, line 4 minus line 3. What you get is the present value minus the present value times U equals the cash flow in year 1 times U. Well, let's undo the U substitution. Most of the times when we do U substitution, we undo it. So now U is back to 1 plus 1 over R. What are we going to do now? Let's factor out PV, or present value, on the left-hand side. And then our final move is to multiply both sides times 1 plus R. And when you do that, you're just going to be left on the left-hand side with PV times R, on the right by C. Now you divide both sides by R, and you've got it. You've got your perpetuity formula derived. All right, so I'm sure the question becomes, do we have to know how to do that? Proof? The answer is no. You should be aware of it. For those of you who enjoy math, this is a good exercise for you in thinking and how you might demonstrate something to be true. But you do need to be able to use this equation, PV equals C times 1 over R, as a shortcut for the present value of a perpetuity. Let's go ahead and look at the derivation for the annuity formula. All right, derivation of the annuity formula. This is a little bit trickier, maybe to think about. There's a good visual for it on page 27 in your textbook, which might just be a little clearer than this, but let me go ahead and try to explain it to you. The first line is what? It's the present value of a perpetuity. In time 0, you want the present value times 0 of perpetuity. So you take year 1 cash flow, multiply times the perpetuity factor of 1 over R. What then is happening in the second line? Well, it looks like there's again, some sort of present value of a perpetuity. See in the bracketed area, it says CF sub t plus 1 times 1 over r, just that chunk. That looks just like the line above it, doesn't it? But it's different. Instead of cash flow at time 1, it's cash flow at time t plus 1. So go back to the first line. If you have cash flow at time 1, that's going to get you the present value at time 0. So if you go back to the second line, the cash flow at time t plus 1, that's going to get you a present value in year t, which is why if you move your eyes slightly to the right, you're multiplying times the t-year discount factor of 1 over 1 plus r to the t, which means that perpetuity, which that first chunk of it makes it become a perpetuity in year t, will now become a perpetuity in year 0 when you multiply it times the t-year discount factor, 1 over 1 plus r to the t. All right. But the cash flow at time t plus 1 is the same as the cash flow at time 1, isn't it? Because in annuities, we have a fixed payment for a certain number of years. The payment doesn't change, so a cash flow at t plus 1 is the same as the cash flow at time 1. So I can certainly rewrite it as you see on the right side of the second line. So let's clarify. Line 1 is a perpetuity with payment starting next year and going on forever. Line 2 is a perpetuity with payment starting in year 4 and going on forever. So line 3, if you look at it, is line 1 minus line 2. It is a perpetuity with payment starting next year minus a perpetuity with payment starting in year 4. Now these are the same size payments. So if you take all payments starting next year minus all payments starting in year 4 going on forever, what you'll be left with is just 3 payments, the payments in years 1, 2, and 3. And if you have a fixed payment that's 3 years long, that's an annuity of 3 years. And you will see very clearly that if you take this calculation, line 1 minus line 2, that boils down to the annuity formula, cash flow in year 1 times 1 over the discount rate minus the 1 over the discount rate times 1 plus the discount rate to the t. There, from the perpetuity formula, we have now derived the annuity formula. All right, folks, I know that could be tricky, and for some of you it's interesting, and the best part of this class is the math. Have a good day.